Welcome to today's lesson, Mastering Motion. Mastering Motion, from graphs to equations. In this presentation, we'll delve into the exciting world of motion, exploring the relationship between motion graphs and the equations of motion. We'll practice interpreting motion graphs and then connect them to the equations of motion for a deeper understanding of how objects move. Get ready to refine your physics skills and become a motion master. Unveiling the secrets of motion graphs. Before we continue on, there is one key term that you need to know. The key term is gradient. A gradient of a graph is the same as the slope of the graph. Now let's continue. Distance time graph. The vertical axis represents the distance traveled, while the horizontal axis represents the time taken. The slope of the line indicates the speed of the object. The steeper slope means faster speed. Speed time graph. The vertical axis displays the speed, and the horizontal axis shows time. The slope of the line reveals the acceleration of the object. The steeper slope represents a greater acceleration. Part 1. How to interpret motion graphs. Decoding the language of motion graphs. To find the distance in a distance time graph, read off the vertical axis. In the speed time graph, find the area under the curve or line. To find the speed in a distance time graph, you have to find the gradient of the line. To find the speed in speed time graph, just read off the vertical axis. Unfortunately, in a distance time graph, acceleration is not directly obtainable. However, in the speed time graph, you can find acceleration by finding the gradient of the line. Note that the gradient is the same as the slope. Part 2. Making graph equations of motion. Bridging graph and equations. Equations of motion. Equations of motion provide a mathematical way to describe and predict the motion of objects. They are essential tools for solving physics problems. 2. Motion graphs. Motion graphs offer a visual representation of the motion of two objects. They provide valuable insights into how objects move over time. Applying the equations. Method 1. Using the equations themselves. Using the equations of motion, we can directly translate the distance traveled and acceleration of an object based on its initial and final speeds and the time elapsed. Do you still remember the equations of motion? Firstly, the distance is equal to speed times time. Secondly, the speed can be calculated by dividing the distance over time. Thirdly, time can be calculated by dividing distance over speed. Note that you only need to remember one of these equations, and you can derive the other two equations from that equation. Method 2. Motion graph. By analyzing the area under the curve and the slope of the line on the speed time graph, we can determine the distance traveled and acceleration of the object. Quick quiz. What is the acceleration of an object? What are its units and how do you calculate it? Did you answer the question correctly? The correct answer is that acceleration is the rate at which the speed of an object increases. Its units, systematic unit, or SI unit, is meters per second squared. You can calculate it by dividing the speed over time. More precisely, you have to find the change in speed or velocity. Part 3. Putting learning into practice. putting knowledge into practice. The Bloodhound HSR aims to achieve a top speed of 1,000 miles per hour. The then vehicle would be timed over a measured mile during its record attempt, which is 1 mile. Visualizing the Bloodhound's journey. 1. Acceleration. The vehicle accelerates uniformly until it reaches the measured mile. 2. Constant speed. Bloodhound maintains the constant speed while traversing the measured mile. 3. Deceleration. After reaching the measured mile, the vehicle decelerates uniformly until it comes to a stop. Calculating the journey's duration. Time for the measured mile. Calculate the time taken to cover the measured mile at a speed of 1,000 miles per hour. The total time for 12 miles. Determine the total time taken for an entire 12-mile journey, considering both acceleration and deceleration phases. Acceleration and deceleration. Calculate the acceleration and deceleration of the vehicle and compare them to the acceleration due to gravity, which is 9.81 meters per second squared. Expanding the challenge. Vary the distance. Explore how the required track distance changes if the maximum acceleration and deceleration are altered. Adjusting speed. Investigate how the time taken for the journey changes if the vehicle's maximum speed is altered. Beyond the classroom, real-world applications. The concepts we've learned about motion, from graphs to equations, are directly applicable to real-world scenarios. Whether it's analyzing the motion of a car on the road, understanding the flight of a plane, or studying the movement of a rocket, these principles are fundamental to our understanding of the world around us. The end. Thank you for watching this lesson. If that is you want, there is an extra exercise that you can do. You, with a partner, discuss some real-world scenarios where you use the concepts we've just learned about motion.